Okay, so for this first one, so there was a really good question about the fact that we have a bunch of new variables and a lot of them basically have the same, they're all P. So just to kind of clarify, so this large P, this capital P is for pressure. And then you'll see this this is technically the Greek letter rho. It's kind of hard to tell, but you kind of want to look just like a little bit closer. So this is when we have a rho, and rho is for density. So rho density basically tells us like how much mass per volume we have. So if we want to figure out the mass of an object, all we need to do is take the density and then multiply it by the volume, right? So if we need the mass and we want to find that, we would have, kilograms per meter cubed, right, for our density rho. And then if our volume, we get that in meters cubed, and that should give us kilograms, right? So that's how we can basically figure out our mass. So that's going to be kind of interchangeable for a lot of the equations. So in this case, they give us dimensions here. So we have a length, we have a width, and we have a depth. And we're trying to figure out the weight of the water. So we have length, width, and depth of basically like this rectangular bed object, right? So in order to find the weight, we need the mass times gravity. So all we have is the density of water. So the density of water from our table up here is going to be, what was our water here? Just 1 times 10 to the third. Okay, so 1 times 10 to the third kilograms per meters cubed, right? For our density. Okay, but we want mass. So what we're going to do is we're going to multiply it by the volume. So our volume is going to be length times width times depth. And then that's going to come out to be 1.20 meters cubed, because our length is equal to 2 meters, our width is equal to 2 meters, and our depth is equal to, what is it, 0.3 meters. Okay. So our mass is going to be equal to rho v, and then our mass for this this square object full of water is going to be 1.2 times 10 to the third kilograms. Okay, so now all we need to do is then multiply that by gravity and we get our weight. So mass times gravity. So our net weight in this case is going to be 1.18 times 10 to the third newtons, or kilonewtons. Or sorry, 10 to the fourth. That's wrong. 10 to the fourth, just a typo on my part. Okay, and that's the net weight of our object. So this is just like a water bed, essentially. Okay, so now we want to find the pressure exerted by the water on the floor when the bed is in a normal position. So we have the same object here, right? And we just want to figure out the pressure on the floor. So we know that our force, right? If we kind of look at how we modeled this guy, we have kind of the weight, we have this as mass times gravity. So that's really the only force that's acting from an object that's just resting on the floor. That's the only force. So if we look up at our equation that we have here, we have pressure is equal to force divided by area. What we're going to do is basically divide, oh, sorry, here. Yeah, we're going to basically just divide it by the area. So then the area in this case, right, is going to be length times width. Okay, and that's going to be 4, right, meters squared. And then the force is going to be equal to mass times gravity, which we found before, right? Newtons. And so all we need to do is just divide those, and then the pressure that is exerting on the floor is going to be equal to 2.95 times 10 to the third pascals for our unit. Okay, and that's our unit this is for pressure. Okay, so I'm going to go ahead and stop this, and then we're going to talk about variation of pressure with depth.